are inclined plane. So this angle is nothing but 90 minus alpha, and the value of beta is 90 minus alpha by 2. So the angle of projection should be the angular bisector of the angle made between vertical plane and inclined plane. Now let's find out the value of maximum range, that is R max. This value comes out to be u square by g into 1 plus sin alpha. Now let's derive this expression. So the value of R is 2u square by g cos square alpha into sin beta into cos alpha plus beta. Now beta is nothing but 90 minus alpha by 2 for maximum range, so R max would be 2u square by g into cos square alpha. Now we can write cos square alpha as 1 minus sin square alpha, and inside the bracket we'll put the value of beta, that is sin 90 minus alpha by 2, and here it will be cos 90 plus alpha by 2. So we have u square by g into 1 minus sin square alpha, which we can write as 1 minus sin alpha into 1 plus sin alpha, and here we can write it as 2 into sin 90 minus alpha by 2 into cos 90 plus alpha by 2. Now 2 sin A, suppose this angle is A and this angle is B, so 2 sin A into cos B can be written as sin A plus B plus sin A minus B. This is a trigonometrical identity. So if we apply this identity here, we'll get u square by g into 1 minus sin alpha into 1 plus sin alpha. Now sin A plus B would be sin 90 minus alpha plus 90 plus alpha by 2, plus sin A minus B would be sin 90 minus alpha minus 90 minus alpha by 2. So alpha gets cancelled out and here 90 gets cancelled out. So finally we have u square by g into 1 minus sin alpha into 1 plus sin alpha into, this is sin 90 degree, which is 1, and this is sin minus alpha, which is minus sin alpha. So we can cancel out 1 minus sin alpha. So finally we are left with u square into g into 1 plus sin alpha. So this is the value of maximum range of a projectile which is projected along a inclined plane, inclined at an angle alpha. So this is our R max. Now let's talk about a special case where the projectile is hitting the inclined plane in the perpendicular direction. So here, as you can see, if the impact of projectile with the inclined plane is perpendicular, that is in this direction, then the component of its velocity along the inclined plane, that is in x direction, will be 0. Now the velocity along x direction can be given as ux plus at, where a is the acceleration along x direction and it is equal to minus g sin alpha. So the velocity along x direction at any given time t is given as ux, which is u cos beta, plus at, where a is minus g sin alpha. So this velocity will become 0 at time t is equal to u cos beta by g sin alpha, and at and this is also our time of flight, because at the end of the flight the projectile is hitting the inclined plane in a direction perpendicular to it. So we can equate this time to the time of flight, which is 2u sine beta by g cos alpha. So from here we can cancel out u and g, so we get sine alpha by cos alpha into sine beta by cos beta is equal to 1 by 2, or tan alpha into tan beta is equal to 1 by 2. So this is the condition for which the projectile will hit the inclined plane. Now we will start the chapter kinematics of circular motion. So first see what is a circular motion. Circular motion is rotation along a circle, that is a circular path or a circular orbit. Circular motion can be either uniform or non-uniform. With uniform circular motion we mean that the angular rate of rotation is constant, and in the non-uniform circular motion the angular rate of rotation is not constant and it is varying with time. Now let's see some definition. First we'll define angular displacement. Angular displacement is the angle subtended by the arc traveled by the object at the center. So let's see this with the help of an animation. So here we can see that this delta S is the arc of a circle, and this is the center of the circle. Let's say this O. So an object travels from point A to point B, making an arc, the length of which is delta S. R is the radius of circle. So as we can see here, this arc makes an angle delta theta at the center. So we can say that the angular displacement of the object when it moves from point A to point B is delta theta. Now let's see what is the direction of angular displacement. The direction of angular displacement is going into the plane for clockwise rotation, and for anti-clockwise rotation it is coming out of the plane. The magnitude of angular displacement is given as delta S by R, where delta is the length of the arc and R is the radius of the circle. And in vector representation we can write delta theta, which is our angular displacement, as R cross delta S by R square. So let's explain this. So here we can see that we can write delta theta as delta S by R, where delta S is length of this arc and R is the radius. Also in vector representation we can write delta theta as R cross delta S by R square. Here the direction of radius vector is radially outwards, so this is our R vector, and direction of delta S is tangential to the arc. So if this is the arc, then the direction of delta S would be tangent to it, so it would be perpendicular to the radius vector. This is our delta S, and this angle is 90 degree. So we can see from here the direction of R cross delta S would be going into the plane for clockwise rotation, and for anti-clockwise rotation the direction of delta S will change. It will be here, and so the direction of delta theta would be coming out of the plane. Now we will define angular velocity. First we'll define average angular velocity. Average angular velocity is denoted by omega, and it is defined as delta theta by delta t, where delta theta is the total angular displacement and delta t is the total time of journey. Similarly, we can define instantaneous angular velocity, which is rate of change of angular displacement of an object. So omega will be limit of delta theta by delta t, where delta t tends to 0, or it is d theta by dt. Similarly, we can define angular acceleration. Angular acceleration is denoted by alpha, and average angular acceleration is defined as the change in angular velocity divided by the time interval during which the change has occurred. So alpha will be equal to delta omega by delta t, or it will be equal to omega 2 minus omega 1 by delta t, where omega 2 is the angular velocity at the end of time interval delta t, at the end of and omega 1 is the angular velocity at the beginning of time interval delta t. Now instantaneous angular acceleration will be rate of change of angular velocity with the time. So instantaneous angular acceleration alpha can be written as d omega by dt. We have already seen various equations of motions in one dimension. We have their counterparts in angular form also. So what we need to do is we can replace the various one-dimensional quantity like final velocity v, initial velocity u, acceleration a, and displacement s with their angular form counterparts. So v can be represented as omega f, which is final angular velocity. U can be replaced with omega I, which is initial angular velocity. A can be replaced with alpha, which is angular acceleration, and s can be replaced with theta, which is angular displacement. So we have this equation. Like if you remember, the counterpart of this equation in the one dimension form would be v is equal to u plus at. Similarly, this is nothing but s is equal to ut plus half at square. Similarly, we have three other equations. So these are almost similar to the equation that we have already seen in motion of one dimension. Now we'll see the relationship between tangential and angular velocity. Tangential velocity is defined as delta s by delta t, where delta s is the length of the arc and delta t is the time interval. So suppose an object is traveling in a circular path and it travels a distance of delta s in time delta t. So we can define tangential velocity, that is v, as delta s by delta t. Now we have already seen that angular velocity omega can be defined as delta theta by delta t, and delta theta is nothing but angular displacement, which is defined as delta s by r. So here we have omega is equal